Let us examine the actual physical model of the semiconductor diode. To understand its operational modes, let us analyze the IV characteristic curve of the diode. First, consider the forward conduction region. Beyond the cutting voltage V sub gamma, the current exhibits exponential growth, whereas between 0 volt and V sub gamma the diode current is negligible, almost zero. We can categorize the IV characteristics into 5 distinct regions. In region 1, the terminal voltage V sub D ranged between 0 and the cutting voltage V sub gamma. Under this condition, the diode current I sub D is practically zero. This state represents the non-conducting subthreshold region or cutoff region. Moving to region 2, where the voltage across the diode exceeds V sub gamma. Here, the diode current I sub D is governed by diode equation I sub S times the quantity e to the power of V sub D over eta V sub T minus 1. In region 2, under strong forward bias, the subtractive unity term minus 1 can be neglected. This region corresponds to the forward bias or forward conduction mode of the diode. In region 3, the applied voltage across the diode is negative, but its magnitude remains smaller than V sub gamma, where reverse saturation effects initiate. Note that parameters V sub gamma and reverse saturation current I sub S are defined as positive values in datasheets. Although the physical voltage polarity is negative on the characteristic curve in region 3, the diode equation remains valid, showing a sharp transition toward the negative reverse saturation current minus I sub S. This transition interval is referred to as knees or curvature region of the IV curve. In region 4, the diode voltage is further negative, where its absolute value exceeds V sub gamma, but remains below the absolute reverse breakdown voltage, denoted as V sub Br. V sub Br specifies the reverse voltage at which breakdown occurs. It is strictly limited. Under reverse bias condition, current flows in reverse from the negative to positive terminal. Consequently, region is formally called as the reverse bias saturation region. If the reverse voltage exceeds the breakdown limit, meaning V sub D is more negative than minus V sub breakdown, we enter reverse breakdown. Because the breakdown parameter is listed as positive in manufacturer catalogs, we explicitly apply a negative sign in circuit equations. In region 5, the diode voltage V sub D clamps near the constant breakdown voltage value, while the reverse current I sub D can carry significantly depending on the external circuit impedance. The diode has now entered the breakdown region, widely known as the Zener or avalanche breakdown region. In practical analog design, diodes are frequently evaluated under small signal dynamic conditions. Let us explore how diode equivalent models are derived in the AC small signal regime. To formulate the small signal model, we express the total instantaneous diode voltage V sub D as the sum of an AC bias component and an AC signal component. Specifically, the DC bias voltage is represented by uppercase variables, while the small signal AC component is indicated by lowercase variables. The total voltage V sub D is superposition of these two terms. Correspondingly, the total diode current I sub D comprises both AC and DC components. Uppercase I sub D represents the constant DC current, whereas the lowercase bold variable denotes the AC small signal current. Please keep these notation conventions in mind. In general, under forward bias operation, the total diode current I sub D is defined by I sub S multiplied by e to the power of V sub D over eta times V sub T. In integrated circuit design, the ideality factor eta is typically assumed to be 1. Setting eta equal to 1, the current equation simplifies accordingly. If the diode is reverse biased or non-conducting in the AC small signal domain, it simplifies to an open circuit carrying zero AC current. However, if the diode is forward biased and on, it is modeled as a dynamic small signal resistance, denoted as lowercase r sub d. How do we calculate r sub d? By definition, the small signal dynamic resistance is the partial derivative of diode voltage V sub D with respect to diode current I sub D. Taking the derivative of the diode voltage yields the dynamic resistance, representing the total incremental state resistance denoted as R sub D. Normally, since current is expressed as a function of voltage I over V, we differentiate current with respect to voltage, specifically evaluated at the designed constant operation point Q. This defines the dynamic conductance. Let us examine an illustrative circuit example. In the circuit shown below, the diode characteristic is given by its IV curve. This solution is provided graphically. The source V sub S is a small signal sinus voltage with an amplitude of 10 millivolts. A 4-volt DC source is connected in series with it. We aim to analyze the circuit under DC bias conditions and determine the amplitude of the AC output voltage V sub out. Regarding capacitor C at the operational signal frequency, we treat it as an ideal AC short circuit. Assuming its capacitance is sufficiently large, its reactance becomes negligible under AC conditions. Okay, let's first analyze the circuit in the DC regime. The capacitor acts as an open circuit and the AC sinus voltage source is deactivated, acting as a short circuit. Let us determine the resulting equivalent circuit. Our AC voltage source is short-circuited and the capacitor is an open circuit under DC steady state. We assign V sub D and I sub D across the diode driven by the DC supply. Applying KVL around the loop, -4 plus V sub D plus 1.6 kilo ohms times I sub D equals 0. From this loop equation, we express V sub D. This defines a linear DC load line. Setting I sub D to 0 yields a voltage intercept V sub D of 4 volts. Conversely, setting V sub D to 0 yields a current intercept equal to 4 divided by 1.6 kilo ohms. Intersecting this load line with the nonlinear IV diode characteristic curve yields the exact quiescent operation point. The current I sub dq is approximately 2 milliamps, evaluated at exactly 1.9 milliamperes. Substituting ID equal to 1.9 milliamps, we obtain the voltage V sub dq, which evaluates to approximately 0.96 volts. Having established I sub dq, we now transition to a small signal AC analysis. The DC battery is short-circuited in the AC regime. The semiconductor diode is modeled purely as dynamic resistance lowercase r sub d, and the capacitor, as defined, acts as a short circuit at our operation frequency. This gives us our small signal equivalent network. Now let us calculate the dynamic resistance lowercase r sub d equals V sub t divided by I sub dq. At standard room temperature, thermal voltage V sub t is taken as 25 or 26 millivolts. Substituting values, 26 millivolts divided by 1.9 milliamps yields the dynamic resistance equal to approximately 13.7 ohms. In the AC model, we observe two parallel resistor branches. Calculating their parallel equivalent resistance yields 0.32 kilo ohms or 320 ohms. Applying the voltage divider rule to determine output voltage V out, we obtain this. Now substituting the values, yielding the output voltage equals 9.6 sine omega t millivolts for the small signal AC voltage. This completes the AC signal response.